everyone. My name is Yiwei. As Steve said, I'm a physics student at the University of Pennsylvania. And this summer I was working with Wael, Farah up at the Allen Telescope Array to develop a GNU Radio SETI data processing pipeline. So just a bit of quick intro to the ATA. It's a radio interferometer composed of 42 6.1 diameter antennae. It covers frequencies from about 1,000 to 15,000 megahertz. And is operated by the SETI Institute at Hat Creek Radio Observatory in Northern California. Its main science goal is to search for technosignatures, which will appear as narrowband signals drifting in frequency over time. And so currently the data processing backend of the ATA will take in antenna data and pass it through custom hardware to produce a raw file, which is then turned into a filterbank or HDF file, which is then analyzed through a software called turboSETI. So turboSETI is a software for asynchronously identifying potential technosignatures. The key function which does the searching is called find Doppler. And what that does is it reads in a header of metadata parameters from the filterbank or HDF5 files. For example, the number of find channels, the first frequency, the observation time, and it maps these parameters to a data matrix found in the file. And then this is what looks for the technosignatures. The problem with this is that turboSETI can only handle filterbank or HDF5 file formats, which poses a problem for users without access to the custom hardware that they have up at the ATA. So why a GNU Radio SETI pipeline? The aim is to have all data processing run from telescope to turboSETI via GNU Radio. And the benefits of this is that it will further the ATA's capability to perform technosignature searches, as well as just make SETI more accessible for amateur radio astronomers and smaller observatories. So the key components of the pipeline we designed with two things in mind. Firstly, we wanted to analyze a high spectral resolution product, but at the same time, secondly, we didn't want to write any data to disk. So under the GNU Radio version of the pipeline, what we have is radio antenna data coming in through the ATA from a USRP source, and then we channelize it first through a polyphase filterbank followed by a fast Fourier transform to produce a NumPy array stored in RAM. After that, we shape this NumPy array into the data matrix that we want in a buffer, and then we apply an adapted version of turboSETI, which doesn't need to analyze filterbank or HDF5 files, but can directly analyze the data matrix in RAM. To do that, we needed to sort of adapt turboSETI. And so here, Luigi, Cruz, and Richard Elkins were very helpful in sort of doing a lot of the developing of turboSETI stream. So this adapts the original find Doppler function from the original turboSETI software so that the user running the Flowgraph can specify metadata parameters in GNU Radio. And the new imaginatively named Doppler finder function would just map these parameters to the incoming data matrix. And this allows us to perform somewhat synchronous analysis on small observation lengths of about 60 seconds. And so a large part of my project this summer was developing the GNU Radio turboSETI module, which currently consists of two key blocks. Firstly, the find ET buffer, which is what shapes the NumPy array running through the Flowgraph into a data matrix, and then passes it into the find ET block, which will run turboSETI stream on the data matrix and tell us if we found anything interesting. So this is an example of the Flowgraph with one channel. As you can see, we have data coming in either from a USRP source or from a recording done with the ATA. It's passed through the polyphase channelizer and then the FFT and then the find ET buffer and find ET blocks. And currently we have this Flowgraph running to about a maximum of 1 megahertz sample rates. Here is a test of the Flowgraph with a Chang'e 5 recording done by Daniel Estevez. So you can kind of see the output of the waterfall plot and the frequency. And this was at a 480 kilohertz sample rate to have a 60 by 480K data matrix. And you can kind of see the output in the command line when running the Flowgraph. So you can see that it kind of gives you the hits. And then here's just a screenshot of the DAT file that it outputs with the metadata parameters specified in the flow graph. Currently, for the one-channel flow graph, the turboSETI search time is between about 1 to 5 seconds, which is pretty good. It's well below the 60-second buffer that we want. And a way to kind of boost the bandwidth is to add more coarse channels in the polyphase channelizer. So here is an example of a 4-channel pipeline. The maximum here is around 4 megahertz, and this also does up the search time to about 15 to 20 seconds, but it's still below the 60 seconds that we want. So the next steps is to begin using the pipeline with the ATA, but also to potentially add a function that will automate the plotting of hits in the find-ET block code. And lastly, just a huge thank you to Luigi, Cruz, and Richard Elkins for their help with turboSETI Stream, as well as Daniel Estevez and Derek Kozel for lots and lots of advice on working with GNU Radio, which is something that I had never done before this summer. And the project was funded by Breakthrough Listen. If you have any questions, I can be reached at this email, and further documentation and code is available on the project GitHub repo. Thank you.